Imagine an ability straight out of science fiction, like the Kwisatz Haderach from Dune, someone who could perfectly simulate every possible future in their environment, you know, charting the absolute best path forward.
Wow.
If you had that kind of power, what would you actually do?
It's a really compelling idea, isn't it? Almost like a superpower for making decisions.
Right.
And what's fascinating is that this isn't just, well, fantasy anymore, this idea. It's becoming the central concept behind what AI researchers are now calling world models.
Exactly. And that's why we're taking a deep dive into it today. We're going to unpack what a world model really is, why it's considered so crucial for developing a truly general artificial intelligence, and then we'll examine the strengths and weaknesses of the current approaches out there.
And finally, we'll introduce you to a compelling new framework that aims to bridge all those gaps, bringing us closer, maybe, to that sci-fi vision.
Okay, let's unpack this. So let's start with this concept of seeing the future. As humans, we kind of do this instinctively, right?
Yeah, all the time.
We're constantly performing these thought experiments or, engaging in hypothetical thinking. Before we even act, we're mentally simulating outcomes.
Like if you're deciding whether to help someone who looks upset.
Right. Your brain quickly runs scenarios. Okay, maybe they'll stop crying, or, I might feel awkward, or maybe they'll be really grateful.
And that lets us tackle this huge range of tasks with just, well, one cognitive architecture. From simple things like controlling our bodies to incredibly complex strategizing.
Fundamental.
That's right. And a world model, or WM, is essentially an AI's internal mental sandbox, its way of imagining those future possibilities.
Okay.
Formally, it's a generative model. It takes what the world looks like. Now let's call that rest for state.
Okay.
And what action the AI wants to try, that's offer after.
For action, right.
And then it predicts what the world will be like next, rest or prime.
Gaspar.
It's like asking, okay, if I do this, what happens? And getting an immediate simulated answer.
So if we already have so many powerful AI systems out there, why is this internal sandbox so fundamentally important for them? What limitation does it address that maybe other AI methods just can't?
Yeah, it's crucial because WMs enable machines to perform these exact thought experiments. They can simulate actions and plans in really complex scenarios, including counterfactual or what-if situations,
What if?
to figure out the best options without ever having to actually try them out in the real world, which would be risky or expensive.
Right.
Think about it. A real-world robot, maybe it has noisy sensors, it can't always perfectly know what's happening. A WM allows it to make sense of that uncertainty and still plan effectively.
Okay, that makes sense.
And this also dramatically helps with knowledge transfer and what researchers call zero-shot capabilities in completely new environments.
Zero-shot capabilities. That sounds powerful. Can you give us an example? What does that actually look like?
Absolutely. Imagine a scuba diver, right? Someone really experienced with moving in low gravity underwater.
Yeah.
That experience, that feel, it might surprisingly help them walk on the moon, where gravity is also low but in a totally different context.
Oh, interesting transfer.
Or think of a mountaineer skilled at predicting treacherous terrain, like where rocks might be loose. They could apply that same predictive skill to strategically plan, say, an ambush in a different environment.
Wow.
Even a skilled gamer becoming an effective drone operator.
Yeah.
They're transferring knowledge gained in one place, often a simulated or simpler one, to a completely new and complex situation.
That's a fantastic analogy. It really highlights how these models become essential when the ground truth world state, what's really happening is either inaccessible or just way too complex for direct real-world trial and error.
Precisely. And a truly general-purpose WM isn't just limited to, physical dynamics like how a ball bounces.
Right.
It could potentially simulate an incredible range of realities, embodied experiences like pain or balance.
Pain. Really?
Potentially, yes. Or emotional states for nuanced social interactions, mental processes like tactics and strategies, those counterfactual what-if scenarios we mentioned, and maybe even evolutionary dynamics over huge timescales.
That's an enormous scope. So how does this simulative reasoning approach stack up against other AI methods we might be more familiar with, like traditional AI logic or even some deep learning approaches?
Well, compared to traditional logical inference, which can be quite rigid, or even model predictive control, which we'll talk more about later.
Okay.
A WM's real strength lies in its flexibility, its generalizability, and its scalability for reasoning.
How so?
Logical inference can break if the rules change slightly. MPC can get overwhelmed by complexity in messy real-world scenarios. But simulative reasoning can adapt. It can adapt to changing computing resources, memory, the environment itself, and the complexity of the problem because it's exploring possibilities across different domains.
Okay.
You could even see something like AlphaGo, the AI that mastered the game of Go.
Yeah, incredible stuff.
You can see that as a specific example of simulative reasoning. It uses a known world model, the rules and board state of Go, to explore future moves and pick the best one.
Right. Okay. So if this is the ideal, this flexible, future-seeing simulation engine, how close are current AI systems actually getting to this? What's out there right now, and what are the limitations?
That's a great question because we've definitely seen a surge in efforts towards building these world models, lots of different approaches. But what's interesting is that despite the diversity, a common thread often emerges. A really heavy emphasis on video and image generation and on the visual quality, how good the generated pictures or videos look.
Right, making things look real. Walk us through some of those examples.
Certainly. So first you have gaming world models.
Yeah.
Things like Genie 2, Muse, Oasis. They can render pretty plausible gameplay videos, but usually only for like a minute or
So
two.
short clips.
Yeah, very short. They're very domain specific, often relying on restrictive inputs like simulated console controls. And they lack the long-term temporal coherence needed for full gameplay sessions, which can go on for hours.
Okay. And then there are things like 3D scene world models, right?
Right.
Like world labs. They look visually stunning.
They do, absolutely. Visually impressive. But they primarily simulate static environments. From what we've seen, they don't typically include dynamic agents, realistic physics interacting, or rich interactivity.
So not much action.
Not the kind you need for complex decision-making that involves cause and effect or multiple things interacting. They're sort of like beautiful but empty stage sets.
Gotcha. What about physical world models? Things like Wave GAIA2 for autonomous driving or NVIDIA Cosmos for robotics, they seem more grounded in reality.
They are, and they show impressive fidelity in low-level physics and sensory motor control. Very good for specific tasks. But they're tightly coupled to their specific domains. GAEA2 is about driving. Cosmos is about specific robotic actions. They can't really address broader, complex, multi-agent or socially grounded worlds outside of, say, driving that car or manipulating that object.
Okay, very specialized. And then the big ones we hear about, the visually stunning video generation models, things like OpenAI's Sora or Google DeepMind's Veo. These models are just amazing at creating realistic-looking footage.
They are amazing, visually. But the key point is they generate fixed trajectories.
Fixed trajectories.
Meaning they create one specific sequence of events, like a movie clip. They don't have explicit notions of state, action, or the kind of simulation control that would allow for counterfactual reasoning, that crucial "what if I did this instead" capability.
So you can't interact with the simulation.
Exactly. They're more of a strict video generation tool focused on pixel-level synthesis, rather than a component designed for intelligent decision-making or planning.
Right. And finally, you mentioned the joint embedding predictive models, like Metafair's JEPA family. These sound conceptually elegant, predicting future latent embeddings instead of raw pixels.
That's right. The core idea is to predict the essence or the abstract representation of the future state, not necessarily all the tiny visual details. It's clever.
But does it work in practice?
Well, the evidence for their practical usability beyond fairly simple toy environments still seems quite scarce. While VJEPA2 has applied this to robotic arm manipulation, which is progress,
Okay.
it's still unclear if they can generalize to more diverse or really complex tasks like, making breakfast or navigating that full-scale mountaineering expedition we might talk about later.
Okay, so it seems like we've seen a lot of progress, definitely, especially in making things look good visually. But is there a common thread here? Like, are they all maybe missing something fundamental in how they approach what a world model truly is?
That's the core question, and honestly, this is where it gets really interesting. Because despite all this impressive visual generation, we argue most current systems are actually missing the fundamental point.
Which is?
What is a world model for? We contend that a WM isn't fundamentally about generating beautiful videos. It's about serving as a sandbox for reasoning and thought experiment.
The simulation part.
Exactly. And most current systems fall short of enabling that kind of purposeful reasoning and planning, usually due to limitations in their scope, their level of abstraction, their controllability, interactability, and ultimately their generalizability. They're often too narrow or too shallow.
Okay, that sets the stage perfectly for a critical look at how people are thinking about building these world models. There's let's say, a vocal school of thought that has put forth some pretty strong claims.
Hmm.
Let's examine 5 key areas where their assumptions might actually be introducing critical limitations for building genuinely general, scalable, and robust WMs. First up, data. Is it all about sheer volume, or is information density more important?
Right. The claim you often hear from this school of thought is that sensory inputs, like all the visual data a 4-year-old processes estimated at a mind-boggling 1.1 exabyte,
Wow.
are inherently superior to text data. They point out that all the textual data used for training large language models amounts to merely 0.9 exabytes.
Yeah.
The argument boils down to more data is better, sensor data is bigger, therefore sensor data is superior.
But if we connect this to the bigger picture, it feels like it's not just about the raw volume, right? While sensory data is massive, a lot of it can be low in semantic content. Think about staring at a blank wall, lots of pixels, not much meaning, and it can be highly repetitive.
Exactly. Whereas natural language, you could argue, is an evolved compression of human experiences. It's incredibly efficient, optimized for abstract communication.
Mm.
Text captures not just physical realities, but also mental states, social dynamics, and even counterfactual phenomena like justice or regret, things which have no direct sensory equivalent. You can't see regret.
Good point. And language gives access to collective human memory, right? Scientific discoveries, engineering failures, history.
Precisely. Think about it. Models trained primarily on text can write software. They can solve Olympiad-level math problems. We haven't seen models trained purely on visual data do anything like that.
So the takeaway here is,
A truly successful world model has to leverage all modalities of experience: text, vision, sound, maybe even touch or proprioception. It needs to understand they reflect different layers of reality. Overemphasizing one, like vision, risks omitting crucial, high-level abstract information that comes through language.
okay, makes sense. Our second critique area is about representation. How should we represent the world state inside the model? Should it be continuous, like a smooth signal, or discrete, like individual words or symbols?
The common claim is that world state should be represented by continuous embeddings, these sort of dense vectors of numbers, not discrete tokens like words.
Okay.
And the main reason given is that continuous values play nicely with gradient-based optimization, which is the bedrock of how we train current deep learning models.
But again, if we look at human cognition,
It offers a really powerful counterpoint here. We instinctively deal with the noisy, variable, continuous stream of sensory input by categorizing things into discrete concepts.
like words.
Exactly, which we then encode in language and symbols. You don't just perceive a continuous blur of color and shape, you recognize a chair or a tree. These vocabulary-based tokens are a huge asset. They offer stability, and they're incredibly composable. You can combine them to build complex, abstract ideas easily.
And LLMs really lean into this, don't they?
They absolutely leverage this. They operate in what you could almost call a man-made latent space of language tokens.
So you mentioned theoretical results. Is there a trade-off with using discrete tokens? Do you lose information?
Well, it might seem like you risk information loss by simplifying to tokens. But some interesting theoretical results show that discrete tokens can actually preserve arbitrary distinctions if you scale them out.
Scale them out, meaning use longer sequences.
Exactly. Increase the sequence length, allowing for longer, more complex symbolic expressions. This turns out to be much more efficient theoretically than just scaling up, trying to make the vocabulary size infinitely large to capture every nuance.
Ah, so length can beat vocabulary size.
In many cases, yes. Length often trumps raw vocabulary size when it comes to capturing rich detail in these token-based systems. So the takeaway: we advocate for mixed representations. Use discrete tokens for robust, interpretable symbolic reasoning, and keep continuous embeddings for that fine-grained sensory nuance. Best of both worlds.
That makes a lot of sense. Okay, next critique, architecture. How should the model itself be built? The claim we often hear is that autoregressive generative models, like the LLMs we use every day, are basically doomed for world models.
Yeah, the argument is they suffer from compounding errors, small mistakes early on snowballs, and they struggle to model outcome uncertainties, like when multiple futures are possible.
And the proposed alternative is often these joint embedding predictive architectures, JETA.
Right, but this raises an important question. Is autoregression really the enemy here?
Is it?
Well, despite appearances, GPA, for all its conceptual cleverness, is still functionally autoregressive and generative deep down. It predicts the next step based on the previous one, so it potentially faces similar challenges.
Ah.
The problem might not be autoregression itself. I mean, many chaotic real-world systems are inherently unpredictable long-term, but well-structured autoregressive models can still learn incredibly useful abstract properties about them.
Okay.
And the concern about reconstructing irrelevant details in traditional encoder-decoder architectures, like predicting every blade of grass perfectly, that's understandable. But simply removing the decoder, like GPA does, can shift the problem. You might end up with indefinability in the latent space because it's very hard to diagnose what the model is actually predicting or why it made a mistake.
It's predicting something abstract, but you can't easily check if it's right.
Exactly. So what's the proposed solution that allows for both structured reasoning and detailed reconstruction without falling into these traps?
What do you propose?
We propose the generative latent prediction, GLP architecture. It's specifically one with hierarchical abstraction.
Okay, break that down. Hierarchical.
Think of it as layers. At the lowest level, for the really fine-grained continuous data, you might use something like latent diffusion models, similar to what creates those amazing AI images, to predict the next tiny piece of sensory data embedding.
For the details.
Right. Then, for symbolic structure, you have intermediate next token predictors, much like how language models handle predicting the next word.
For the concepts.
Exactly. And finally, for the grand strategy, the long-term goals, you leverage powerful LLMs operating in almost a thought space, where the AI can plan much further ahead.
So it combines different prediction methods.
Yes, it allows for both structured reasoning and detailed reconstruction when needed, mitigating that error accumulation problem, and effectively mixing both continuous and discrete representations at different levels.
All right, let's move on to the fourth critique. The learning objective. What exactly should a world model be trying to learn? The claim here is to ditch traditional probabilistic data reconstruction objectives, where the model tries to perfectly recreate the input data.
Like predicting the next video frame pixel by pixel.
Right. And instead, adopt energy-based latent reconstruction objectives, predicting that abstract embedding, supposedly for better tractability.
But this raises a really important question. Why learn only in that abstract latent space instead of grounding the predictions in the actual observable data?
What's the risk?
Latent reconstruction loss, where you
Yeah.
compare predicted latent states to the encoded ground truth without a decoder to turn them back into something observable like pixels or sound. Well, it's known to be prone to collapse.
Collapse.
Yeah, it's a failure mode where the model finds a loophole. It trivially minimizes the loss by mapping everything to basically the same constant point in the latent space. It learns nothing useful. You often need complex, hard-to-tune mathematical tricks, regularizers, just to stop this from happening.
That sounds problematic.
It can be very tricky to get right. But in contrast, a generative reconstruction loss, which does use a decoder to ground the predictions back in observable data, like generating the next frame or sound, it naturally avoids this collapse.
Because it has to produce something sensible.
Exactly. It provides a much more stable, interpretable learning signal. It's like checking your work by seeing if the answer actually looks or sounds right.
Okay, but is there a deeper connection?
There is. And here's the critical catch, which we formalize mathematically. Latent reconstruction is what we call an upper bounded surrogate for generative loss.
Upper bounded surrogate. What does that mean in simple terms?
It means that minimizing the latent loss doesn't guarantee you're minimizing the real-world error. The latent loss can be low even when the generated output is actually garbage from a semantic perspective. It can miss important mistakes that a generative loss, by trying to reconstruct the observable world, would immediately penalize.
So the model might think it's doing well in abstract space, but its predictions don't match reality.
Precisely. A world model must learn from the pixel space and sound space, etc., not just in its abstract latent space, to ensure its internal representations are meaningfully grounded and robust enough for the real world.
Okay, really important point. Finally, critique 5. Usage. How should these world models actually be used to make decisions? The debate often pits model predictive control, or MPC, against reinforcement learning, RL.
And the claim often made is that MPC is favored over RL for using WMs, mainly because it's considered more sample efficient, you need fewer real-world trials, and potentially safer.
Okay, what's the counter-argument? Does MPC have downsides?
It definitely does. While MPC learns from offline data, which is good, it suffers from very high computational overhead at inference time when it actually needs to make a decision.
So it's slow.
It can be very slow, especially for fast-changing environments. It also typically plans only a few steps ahead, maybe 10 or 20 steps. It really struggles with long planning horizons because those prediction errors can accumulate and explode over time.
Right, the compounding error problem again.
Exactly. And it also tends to rely on fairly simple methods for proposing what actions to even consider simulating. It's worked well in simplified, predictable settings, like the game of Go we mentioned.
Where the rules are fixed.
Right. But it often struggles with the complexity and unpredictability of the real world.
So, if MPC has these limitations for complex, dynamic environments, what's a more scalable and flexible alternative for actually using these world models effectively?
Our view is that reinforcement learning, RL, used in conjunction with a world model, offers a more general, flexible, and ultimately scalable approach.
How does that work?
It cleverly shifts the heavy computational cost. Instead of doing all the simulation at decision time like MPC, you do it during the training phase. You use the world model offline, like a simulation engine, to train a separate policy network.
And that policy network.
That policy network learns to predict the best action directly from the current state. So in the real world, when a decision is needed, the policy network can provide very fast action selection.
So the thinking happens beforehand.
A lot of it, yes. This setup allows for much longer-term strategic reasoning because the policy can implicitly learn from many simulated trajectories. And it's much more applicable in highly complex settings like goal-conditioned robotic manipulation or autonomous driving in busy cities.
So both have their place, maybe.
Absolutely. Both MPC and RL have value. But RL, particularly when paired with a WM, truly enables learning from these imagined worlds for continual improvement and adaptation, which feels much closer to how humans often practice things mentally.
Okay, this deep dive into the critiques really sets the stage. It all leads us logically to the new framework you're proposing. Drawing from all these critiques on existing approaches, you're previewing a new architecture. PAN, which stands for a physical, agentic, and nested world model.
That's right.
Tell us about its core design principles, building on what we've just discussed.
PAN is built on 5 key design principles that directly address those critiques. First, use data from all modalities, not just vision. Incorporate text, sound, touch, internal states. Second, employ mixed, continuous, and discrete representations to capture both nuance and structure.
The best of both worlds.
Third, adopt a hierarchical generative model, specifically using an enhanced LLM backbone for high-level reasoning and a diffusion-based predictive module for low-level details, that GLP architecture we talked about.
Got it.
Fourth, crucially, train with a generative loss, grounded firmly in observation data. Make it predict the actual sensory experience.
Avoids collapse.
Exactly. And fifth, apply the WM primarily to simulate experiences for training agents using reinforcement learning, enabling that fast, flexible decision-making.
Okay, that sounds like a comprehensive approach. Now, to help us understand PAN better, let's dive into a motivating use case you've highlighted. A complex mountaineering expedition. Why pick such a challenging task?
Yeah, it's an ambitious example, but it's ideal because it really reflects the full complexity of real-world reasoning demands.
Oh, so?
Think about it. You have truly multimodal data sites, sounds, wind, temperature, the feel of motion and balance, and even internal senses like pain or fatigue.
All senses involved?
Absolutely. It covers a vast spatiotemporal scope, too. From split-second decisions like precisely placing your hand on a rock face to days or weeks of strategic route planning across an entire mountain range.
Huge range of scales.
It requires varied action granularity, from fine motor control for gripping an ice axe to high-level strategic decisions about campsites or weather windows. This is absolutely not a toy task like moving blocks.
Definitely not. So how would PAN actually simulate something as incredibly complex as a mountaineer's experience? What does that look like internally?
Well, imagine the mountaineer. They need to constantly internalize all these sensory inputs, right?
Yeah.
And then crucially, they need to simulate future states for all sorts of tasks.
Like what?
Like selecting the right gear for an upcoming storm they anticipate, planning the safest route up a technically difficult or dangerous section, assessing the microclimate on a slope for potential avalanche risk, or even predicting in that split second the best, most stable hand placement on a slippery, wet rock face.
Wow, that's incredibly rich.
It is. And PAN is designed specifically to handle this kind of rich, multi-layered simulation across different timescales and levels of abstraction.
So let's get into the nuts and bolts. How does the PAN architecture work in action? Let's start with how it takes in all that diverse information.
Okay, it begins with the sensory encoder. This module ingests all those multimodal signals we talked about, visual, auditory, tactile feedback, maybe even internal states like perceived pain, balance, or hunger signals encoded somehow.
Okay.
And it maps them into both discrete tokens and continuous latent embeddings simultaneously.
A mixed representation.
Exactly. Discrete tokens handle the abstract concepts, often using natural language words, things like where am I, what tools do I have available, what is my current emotional state, giving it clear symbolic hooks.
And the continuous part.
The continuous latent embeddings capture the fine-grained, nuanced perceptual information, the specific texture of the rock underfoot, the subtle shift in wind direction, the precise color of the ice.
Okay, so you have this rich, mixed input representation. Then comes the core reasoning engine, the world model backbone. How does that work with these mixed inputs?
Right. This is the heart of Pan, where the simulation happens. It's built on two main components working together. First, an enhanced large language model for the high-level conceptual language-based reasoning. This lets it think about long-term strategy, abstract goals, and symbolic planning.
The strategist.
Exactly. But then it also has a diffusion-based next latent embedding predictor. This handles the fast, low-level, almost subconscious embodied responses, like intuitively knowing how a particular foothold feels and adjusting balance without consciously thinking, I must shift my weight.
The intuition part.
Kind of, yeah.
Yeah.
And crucially, there's a mechanism, we call it a learned switch, that adaptively combines the outputs of these two components based on the current task commands.
So it can shift focus.
Yes. It gives Pan the flexibility to be both a deliberate, long-term strategic planner and a highly reactive embodied agent responding to immediate sensory details. This is really a concrete instantiation of that generative latent prediction, GLP architecture we discussed earlier.
And you mentioned it has a multimodal decoder. You stressed this was important for avoiding those collapse issues. How does that work here?
It's absolutely crucial. This decoder takes the predicted internal state from the backbone, that mix of tokens and embeddings, and its job is to reconstruct the full sensory experience of the next expected observation.
Not just video.
Not just video. It tries to predict the sound, the temperature, the motion, maybe even the simulated pain or fatigue signal, the text describing the situation, everything that was input for the current state, it tries to predict for the next state.
Wow.
This generative supervision, trying to recreate the observable world, is what grounds the predicted world state firmly in sensory reality. It ensures the internal representation retains all the necessary information and avoids those collapse issues we saw with latent-only prediction objectives.
So the model's predictions have to make real-world sense.
Precisely. It means the model truly has to understand the observable consequences of its simulated actions.
And how does this complex architecture lead to efficient training and data use? It sounds computationally intensive.
It can be, but Pan uses a kind of divide-and-conquer approach. Individual modules, like the encoder or parts of the backbone, can be pre-trained on relevant data and then aligned together.
Okay.
And it's potentially remarkably data efficient because of its multi-scale view of the world. For example, it doesn't need pixel-level detail predicted perfectly when planning a route across a mountain visible from miles away. But it can focus in on that detail when simulating the precise feeling of a hand placement on a rock.
It focuses where needed.
Right. General capabilities, like strategic thinking, can be learned from abundant language data, while specific embodied skills might come from more targeted physical interaction data, perhaps from robots or simulation.
Okay, so finally, how does this all come together to enable practical, agentic reasoning with Pan? How does an AI actually use this sophisticated world model to, say, climb that mountain?
Right. Imagine an agent powered by Pan, prompted with a goal like reach the summit safely. It uses the Pan WM as its rich internal sandbox. Before even taking a step, it can pre-compute and cache a diverse set of possible future world states and the simulated outcomes of different action sequences.
Planning ahead.
Exactly. It simulates various paths, potential weather changes, possible obstacles like crevasses or rock falls, and stores those potential outcomes. Then, at decision time, when it needs to act quickly, the agent consults this cached, imagined world.
Like checking its notes?
Sort of. This enables more deliberate, adaptive, and selective planning because it decouples the potentially slow, expensive, real-time simulation from the immediate action selection.
Faster reactions.
Potentially much faster and more considered reactions. It really starts to mirror human-like cognition. We plan ahead, we anticipate, we navigate uncertainty based on past experience and mental simulation, and then we act with flexibility and foresight. It's like getting closer to that Kwisatz-Haderach ideal, but grounded firmly in our complex, messy, multimodal reality.
So, wrapping this up, what does this all mean? We've taken quite a journey here. We've seen that a world model isn't just about, generating stunning visuals. It's fundamentally about simulating all sorts of possibilities in the real world, physical, social, mental, for purposeful reasoning, planning, and transferring knowledge.
Right. And while the current approaches out there have made really important strides, especially visually, the PAN architecture offers, we think, a compelling pathway towards truly robust general-purpose AI. It does this by deliberately combining diverse data modalities, using mixed representations, employing that hierarchical generative modeling, and insisting on observation-grounded learning through generative loss.
It really feels like a more holistic approach.
We hope so.
Which leads to a final provocative thought for you, the listener. What new frontiers of problem solving, what kinds of complex challenges could AI unlock if it could truly imagine and choose from every possible future? Maybe not perfectly like the Kwisatz Haderach, but effectively grounded in our incredibly complex multimodal reality. What becomes possible then?